Okay. Can you hear me? Yeah. Okay. Hello. Hi. So I'm Lavinia Chiara Tagliabue. I work for the University of Turin, Department of Computer Science, and today I'll talk about this study that we are doing in the research of improving the efficiency of a critical infrastructure, which is the HPC, high performance computing at the University of Turin. We have this computer that is used for, it's called HPC for AI because it supports AI computing and a lot of loads that are coming from the university and also external to from other industry partners. We are working on a BIM-based framework for real-time monitoring and decision support, and we have this project included in an European founded project that is called DYMAN, and my colleague Robert Birke is the coordinator of this project for our university. I'm the delegate of director about the digitalization of the built environment, and Professor Aldinucci is the delegate for AI. And then we have Silvia Meschini and Viviana Vaccaro that are our assistant in the computer science department for our sector. So we are using this data center that you can see here, our case study, the HPC for AI. In Turin. Turin is close to Milan in the north of Italy. I'm not sure if you are familiar with the place, but we have a university with 125 buildings, and this department is not in the central area of Turin, but we have a lot of space, and we created this HPC that is close to our offices of the department. And as you can see, we choose also a layout that can give transparency to the infrastructure and to be visited by industries, students, and collaborators on the territory. So this is a very important infrastructure, and it's a case study of this European project. We have different kind of cooling system performed by the Vertiv unit that is located on the rooftop of the building. And you can see here that we have the free cooling, evaporative, or mechanical system that can be adopted to improve the efficiency. The PUE is the coefficient that is used to evaluate the efficiency of the data center. It's very, very good for this kind of infrastructure because one of the goals of the realization is to be as green as possible, let's say. So this was one of our main goals, and as you can maybe know, data centers are one of the infrastructure that have a lot of importance now on the consumption aspects, and the consumptions are growing. And for that reason, it's important to try to understand how they are working and how to optimize their behavior, energy behavior, and thermal consumption. So we created this digital twin for the data center in the European project. And why do we need it? Because we want to have the real-time visibility of the data of the data center in the electrical consumption and also in the condition of the system that is providing the cooling. We are also testing technologies for improving the cooling system. And so we created a BIM model that is used as a backbone of the digital twin, and we connected in real time the data of the sensor that are on a different platform proprietary of the Vertiv system. We want to also simulate scenarios because, as I mentioned, we are testing different cooling systems and possibility to improve the efficiency. We are also checking the loads that are very variable in the calculation and the computing effort of the data center, and so we need to predict and anticipate this kind of consumption. And also we want to have a closed loop optimization and trying to have a feedback and alert and maybe strategies to improve the efficiency in an autonomous way. So we have in this moment a fragmented monitoring system with different proprietary platforms that are including the spatial information, the data, and the semantic information of the building and operational data. And the BIM model is used not as a static system, but as a dynamic base for the digital twin. So these are the research question and contribution that we are trying to achieve in this project. Is the modular layered architecture, automated BIM to IoT synchronization, and persistent parameter-based sensor ID mapping that we are using for the connection of the sensor data to our model. And then we have a predictive control fully embedded in the BIM environment, created with the Dynamo. So we are creating also a predictive system that can give us information about the consumption. Here is the layers of the architecture. We have the physical layer where we have the sensor, the infrastructure, and the Vertiv unit for the cooling. Then we have the data management layer that is an influx DB database that is then connected to our sensors in the virtual environment. And then we have the integration and synchronization layer through Dynamo, Graph, and Python scripts. And we are using the ASHRAE regulation for checking the thresholds of data and possible alerts that can give us information about possible correction action that we have to adopt for the system. The digital representation layer is the BIM model with the shared parameters and view filters that can give us different information about the functioning of the system. And then we have this model predictive control engine that is based on a resistive capacity thermal model and algorithms to optimize the exchange of heat inside the system. Here you can see some part of the system. We have the physical sensing. Here we have the sensor in the area of the data center and the influx DB database where we are collecting the information of indoor environmental condition of the data center. We have the data of the weather station, so outside condition, inside condition in the data center, and also in the offices that are around, because, okay, we have to speed up. This is the schema, so we have the Revit model that is used for the BIM visualization, the sensor data storage, and through the Python and Dynamo visual programming language application, we are transferring the data and organizing this workflow for the data acquisition from the influx database. Then we have the parameter updating into the model, the threshold checking that is used for the anomalies and alert that we can have, and sensor validation. I go a little bit fast, so we can maybe have time for a question. Here you can see the model and some shared parameter about the sensor that are inside. And here we have the list of the racks. I don't know if you're familiar with the structure of the data center, but here you can maybe understand better. We have, in this case, the information about the rack temperature. So we have sensor on each rack. We have 16 racks here, and we are checking if the temperature is correct according to the ASHRAE requirement. And here we have the automatic tables and alerts that are giving us the severity of the threshold, the condition, and the window of time. And we are counting the possible data that are out of the threshold. Here are the ASHRAE alerting conditions. So they are giving us the rule-based organization of the checking and evaluation. And here is the reconstruction of the information flow of the data acquisition, data structuring, and views that we are automating into the BIM model. And so we are checking the EFC performance. EFC is the Vertiv system that we have for the cooling. And here we organized all the information in this table where we are checking the component status, if it's working in the cooling or free cooling, evaporative cooling, or a mechanical ventilation condition here. And then we have the anomaly review, the thermal condition, and all the logs for the 24 hours. So here is the part of the predictive control engine. In this moment, we started with this model that can evaluate, it's simulating which will be the PUE in the next 60 minutes. And as you can see, we have quite good accuracy of this predictive control engine, and we are now working on improving it with other possible algorithms. And here we have the structure of the data that are read in the InfluxDB, the predictive engine. We can write the data into the sensor in Revit and the data of the server room, and we have the validation. So as I mentioned, all the system is embedded in the BIM. Yeah, let's go. Here it's just the RC thermal model that is a traditional equation for thermal systems. And we did a model calibration using 1 month of operation. Here you have the data set and points. And yes, we are using it. So this system not only for visualization, but for active support of the decision, for optimizing the critical infrastructure. So our scope is to create a framework that can be used in different kind of building. That could be university, HPC facilities in our case, or hospital server rooms, office building, or educational and financial institute data center. We know that now everyone has a data center. Our data center is not so big, but it can be a replicable framework. These are the future work, so we are going ahead with the calibration. We want to apply a machine learning-driven optimization and checking it with sustainability KPIs. We are also working on LCA of the data center and possible evaluation in the sustainability rating system. Here is the team, and thank you for your attention. I don't know if you...
It's a lot of information.